Greetings, Saintsman. This is lesson 11.3 regarding the areas of polygons. So first thing, we're going to actually discuss two area formulas. First one, we already know how to find with regard to areas of a quadrilateral. We already know how to find the area of a square. We also know how to find the area of a rectangle. We could actually find the area really of any polygon by doing composites, as you saw probably in that last lesson, 11.2. If we subdivide it, and you guys already know how to find the area of a triangle. So you could take any figure, right? And then you can make it into a series of triangles or even quadrilaterals and triangles. Here's one for you which we don't have, which is finding the area of a rhombus or a kite, which is going to have the same formula. What we're going to do is we're going to take 1/2 of the product of the diagonals in order to find it. So let's take a look here. It's going to be pretty straightforward. I'm going to draw a kite. Remember what a kite is? Kite is going to have a pair of congruent sides that are going to be adjacent. All right. So here we go. Remember, this is just one of those other facts about it is that those diagonals are perpendicular. If we're going to find the area, what we're given in this problem is that this length here is 11 feet, and this horizontal length right here is 5 feet. So when we go to solve, when we find the area, what we're going to do is we know that the area is equal to 1/2 of the product of those two diagonals, and those diagonals are that horizontal length 5 and the vertical length 11. So 1/2 of 55 times 11, which is 55 over 2 feet, which we could write, or of course you guys could put that in decimal form, which is 27.5 feet. Now again, I'm going to get the question, and I'm answering it now, but I'm going to get it in person, which means you're not really paying attention during your videos, which is, Mr. Granados, do you want I thought you hate decimals. I thought you don't want a decimal answer. No. I don't want an approximation. This is not an approximation. It's an exact answer. 27.5 is exactly 27.5. Let's do another one of these here. Let's take a rhombus. Right? So remember, a rhombus is a quadrilateral where all of the sides are congruent. Okay? So here's your rhombus. Now, here's the diagonal here, which is going to be 10 millimeters. And then we have another length here, which is 24 millimeters. And we're going to find the area. And it should be pretty straightforward. All right, it's going to be 1/2 of the product of those diagonals, which is 10 times 24. 10 times 24 is 240, divided by 2 is 120 millimeters squared. All right, so some of you guys are thinking, oh man, that's just so quick, so easy. I'm glad you feel that way. But now we're going to get to the bulk of what we're going to do. So now, gentlemen, you can find for effectively any quadrilateral, and even if you wind up subdividing, if you have the adequate amount of information, you can make it into triangles, and we know the area of a triangle is 1/2 of the base times the height, that perpendicular height or altitude. What we don't know, though, is how to find it for pretty much any polygon. So for all regular polygons, we have one formula that works for area. Yeah, one formula. Your area is equal to 1/2 capital P times lowercase a. What these letters stand for, P, of course, is going to be the perimeter, that length around. But what we don't know is how to calculate this length A, which is the apothem, not to be confused with the apothem. All right. We don't say apothem because this is not some sort of a creature you find in the road. This is the apothem. It's the proper pronunciation. This is how you find that particular distance here. So I'm going to show you guys. I'm going to inscribe a pentagon, a regular pentagon, into a circle. Okay? Now, what does that mean? If it's a regular pentagon, it means, and this is what you can use this formula for, it's only for regular polygons. It means that all of my sides are congruent. All right? All of my sides are congruent. Here are the portions of it. One, this length right here from the center of your polygon to that angle, that interior angle. This, of course, oops, yikes, guys, sorry about that. This, of course, is what is going to be referred to. Now, think about it. If I didn't have the inscribed polygon there, that would just be the radius. And that's also what we're going to call that length here. From the vertex of the interior angle to what would be the center of the inscribed circle or the circumscribed circle about the regular polygon. Now, what I don't have here is this length right here, which is a perpendicular altitude. Gentlemen, this is what is referred to as the apothem. Okay, that is your apothem. All right, so how would we go about solving this thing? Well, let's think about it. Do we have any tools at our disposal? Well, if this is a regular polygon, remember that you can find the interior angle, right? It's 180 times n minus 2 divided by n, and it'll give you a singular interior angle. Now, that interior angle, that radius will divide it by 2, okay? So we could have think about what we have here. We have a right triangle then. If we have a degree measure, and again, let's do this guy real quick, right? So there's 180 times 5 minus 2 over 5. And you punch that into your calculator, right? So 540 divided by 5, which is 108 degrees. So when you take that angle measurement, that applies for that interior angle. But here, this is going to be half of that because it gets bisected by that radius. So that's 54 degrees. If I know that in a right triangle, can't I, if I know just a singular length, or even here, right, of your pentagon, for one of those sides, for the regular pentagon, well, they're all going to be the same. I could find, going back, remember in my formula, which is back up here, what area is 1/2 of the perimeter times the apothem. Perimeter, right, I would just multiply this entire length by 5, right? And then to find my apothem, I could take this bisected length, and I could use trigonometry, right? SOHCAHTOA with that interior angle measurement for that triangle, that right triangle, 54 degrees, to solve for what that apothem is, right? Given that I have the opposite, I'd have the adjacent side, and I would just need to calculate the opposite. Yes, we are going to wind up using some trig. It's back in our lives, and it's a good thing. So let's do a different problem. One I think you're just going to like a little bit better. So I'm going to draw a regular hexagon. And we're going to find the area. And this is all that we're given. Is this length right here across. This entire thing is 32. All right? So, remember, my area is equal to 1/2 of my perimeter times my apothem. Now, if that's the case, here I have 16. Okay. Well, the entire thing is 32. Take this length right here and see if we can figure out more about this. Well, if this is a hexagon, right, all the interior angle measurements are 120, right? If I go through, right, 180 times n minus 2 over n, okay? So 6 minus 2, 4, right, times 180 divided by n. And it'll give me 120. And check it out. What does that mean? It means that this right here, just this angle is 60, meaning the other angle, the other acute angle, has to be a complement, which is 30. Gentlemen, look what we have. We have a 30, 60, 90 triangle. All of these lessons now coming back together, right? And if that's the case, the relationship to go from the hypotenuse to the short leg is you divide by 2. So that's 8. Meaning this bisected side, whole thing is going to be 16, which matters to us, right? Because we're going to say 1/2 of the perimeter, which is 6 sides times 16, right? And now we have to just multiply times the apothem. So let's solve for what that is. Well, how do we go from short leg to long leg? Well, that apothem is going to be the short leg times rad 3, or in other words, 8 rad 3. How great is that? And then we just find our product at 1/2 of 6 times 16 times 8 rad 3. And that's going to be 384 rad 3 units squared. All right, let's do another one of these. Let's do one that's got some trig in it, okay? That was some light trig that we had with the old 30, 60, 90. And here is what's fun about these is they're not going to even draw us a diagram. We're going to find for a regular nonagon, has sides of 6 inches, not inches, inches. What is the area? Struggling here to type. There we go. All right, well, remember, for all regular polygons, the same formula, area is equal to 1/2 of the perimeter times the apothem. Well, we can find the perimeter quickly, right? Nonagon means 9 sides, right? So, if it's all 6 inches, 9 times 6, and then we still have to multiply times the apothem. So that's what we got to find out. So, this is what I always draw. I don't even draw the whole nonagon, because it's going to be redundant. I only need a portion of it, which is going to be from the center, and then there's just like this little bottom part. So it's almost like a little zoom in. Like I'm back up here and I just zoom into this part, right? So here's my little zoom in right here. Well, I know my entire side here is 6. So I need to find this apothem, okay? And if this is 6, then this short side right here is going to be 3. Now, I could find A given if I used trig, and I'm going to need to figure out what are my lengths here. Now, remember, I can figure out my exterior angle off of this bad boy from 9 sides. It's going to wind up being, right, 360 divided by 9, which is 40 degrees, right? So this is 40. This is the other way, rather than doing 180 times n minus 2 over n. Okay, I could do that, but I'm not going to do that here. At 40, meaning this entire thing is going to be 140, right? Yikes. Oops. I deleted too much. Here we go. Meaning this guy right here is going to be 70 degrees. Meaning this one up here is going to be 20. Now, think about what I have here. From the angle, I could work from 70. From the angle, I have this and this. What parts of that when we go to and do toa? Well, it's toa, right? It's opposite over adjacent. So we can say that the tangent of 70 is equal to that apothem over 3. And we can solve for the apothem by multiplying both sides by 3. So 3 times the tangent of 70 is my apothem. That's it. So I go back here and I plug that in. 1/2 of 9 times 6, which you guys know is 54. Times my apothem, which is 3 times the tangent is 70. All right, then I just multiply that whole thing out. 1/2 times 54 times 3 means I have 81 times the tangent of 70 inches squared, and that is your answer. That's your exact answer. You can punch it in your calculator. It's going to spit out an approximation. Good for you. But if you don't have this exact answer, it is all for naught. So trig came back. If you didn't really work hard at it, it's going to be difficult for you to be successful. I know like a good chunk of you guys, though, did pretty well this year with that. So if you have any questions, of course, come see me during my office hours. Good luck.